The primary purpose of power system protection is to detect faults within the electrical network to ensure the safety, reliability, and efficiency of the power supply. Faults, which can occur due to various reasons such as equipment failure, natural disasters, or human error, pose significant risks to both the infrastructure and the people relying on the power system. By detecting these faults promptly, the protection system can isolate the affected sections, preventing the spread of damage to other parts of the network. This isolation helps in safeguarding expensive equipment like transformers and generators from severe damage, thereby extending their operational life and reducing maintenance costs. Additionally, quick fault detection is crucial for maintaining the stability of the power grid. Unchecked faults can lead to cascading failures, resulting in widespread blackouts and significant economic losses. By ensuring that faults are detected and managed swiftly, power system protection minimizes downtime, ensuring a continuous and reliable power supply to consumers and businesses. This reliability is not only essential for daily operations, but also for meeting regulatory standards that mandate high levels of service quality and safety. Overall, the ability to detect faults effectively is fundamental to the economic and operational efficiency of the power system, as well as to the safety and well-being of the community it serves. Purpose of power system protection is to detect faults or abnormal operating conditions. Relays must be able to evaluate a wide variety of parameters to establish that corrective action is required. The most common parameters which reflect the presence of a fault are the voltages and currents at the terminals of the protected apparatus, or at the appropriate zone boundaries. Occasionally, the relay inputs may also include states open or closed of some contacts or switches. A specific relay, or a protection system, must use the appropriate inputs, process the input signals and determine that a problem exists, and then initiate some action. In general, a relay can be designed to respond to any observable parameter or effect. The fundamental problem in power system protection is to define the quantities that can differentiate between normal and abnormal conditions. This problem of being able to distinguish between normal and abnormal conditions is compounded by the fact that normal in the present sense means that the disturbance is outside the zone of protection. This aspect, which is of the greatest significance in designing a secure relaying system, dominates the design of all protection systems. For example, consider the relay shown in figure. If one were to use the magnitude of a fault current to determine whether some action should be taken, it is clear that a fault on the inside fault F1, or on the outside fault F2, of the zone of protection is electrically the same fault, and it would be impossible to tell the two faults apart based upon the current magnitude alone. Much ingenuity is needed to design relays and protection systems which would be reliable under all the variations to which they are subjected throughout their life. Whether and how a relaying goal is met is dictated by the power system and the transient phenomena it generates following a disturbance. Once it is clear that a relaying task can be performed, the job of designing the hardware to perform the task can be initiated. The field of relaying is almost 100 years old. Ideas on how relaying should be done have evolved over this long period, and the limitations of the relaying process are well understood. As time has gone on, the hardware technology used in building the relays has gone through several major changes. Relays began as electromechanical devices, then progressed to solid-state hardware in the late 1950s, and more recently they are being implemented on microcomputers. We will now examine in general terms the functional operating principles of relays and certain of their design aspects. Detection of faults in general. As faults short circuits occur, currents increase in magnitude, and voltages go down. Besides these magnitude changes of the AC quantities, other changes may occur in